This is an example where we practice rotational dynamics in the context of a previous example that we did way back in chapter 7. So in chapter 7, we did this Atwood's machine problem. So that means we have a block of mass M1, and it's over the pulled eventually over the edge by a massless rope attached to a pulley, or hung over the end of a pulley, and you got a mass. You got a mass M2 that is hung over the edge. Okay, and the pulley's massless, and the rope is massless, and there's no friction, and so when we analyzed this problem using Newton's third law, we just took the typical free body diagram for M1, which was normal force up and mg down, tension pointing to the right, and that tension matched up with the tension that was pulling up on M2, with M2g down, F net down, and we summed the forces. Again, this is just a quick review, where we get T equals M1A, and then T minus M2G equals minus M2A. That's summing the forces for the first block in the X direction and the second block in the Y direction. Certainly could use N minus Mg equals 0, but that's not relevant to this equation or to this problem. And so we had two equations, two unknowns. Typically, you're given the values of the masses, and you know G, so you can use substitution to find A. And when we solve for A, we get A equals M2 over M1 plus M2 times G. And then we can also get an expression for the tension, which is pretty straightforward from there. So that was the chapter 7 problem. Now, I want to revisit this problem in light of chapter 12. And to do that, we're going to instead of having it be a small massless pulley, we're going to have it be like a big drum that's being pulled by the bottom block. So here's still one, and then something like this. All right, so it's got a, some pulley, it's still attached in some way, and then it falls, it's hanging. So you got block 2 hanging. And so in looking at this problem, it is certainly different because now you have a very big wheel that you need to turn. Maybe it's like a flywheel, or maybe it's like a turbine, or maybe it's like a big part of a windmill. So basically, it's a rotational object. It has a radius r, a mass m, and so we want to know how that massive pulley changes the problem. It's still massless or smooth surface, and all the other approximations that we're familiar with. We're going to keep the rope massless, and we'll still have very little friction in the mass and the pulley, or in the ropes and the pulleys. So how does this change? If you look at the blocks 1 and 2, those free body diagrams for the most part stay the same. So you've got N up, M1G down as usual. Don't forget your vectors, your vector caps, and then T. But one new thing that's different is that the tension on the rope, horizontal part of the rope, has to be different from the tension on the vertical part of the rope. And so this is T vector T1. And on the block right here, that is vector T2, tension T2. It's still smaller than the gravity vector M2G. So you got F net still pointing down 2. So that's the only difference between 1 and 2 in this example. But now we have a third object in the system. This massive object now is included in the system. And so all the external forces can exert torques on it. And so let's draw a sort of rigid body diagram for this block. So circle. Now, what are all the forces acting on this pulley, on this big drum? Well, there's certainly gravity acting at the center of mass, which we indicate with a circle plus. So capital M times vector G pointing down. We've got now Newton's third law, we have a T sub 1 pointing backwards. And this is a third law pair. And then we've got a T2 pointing downwards. Once again, another third law pair. This tension vector over here aligns with the tension vector at the bottom. Oops. But that's not all the forces acting on the pulley or on the big drum, because these forces add to something that points, down and to the left. And so we need to have at the axis, we need to have some sort of support force, F sup, which will make the net force on the wheel 0. So in this case, we've got F net equals 0, but tau net is not. So the net torque is going to be a non-zero. And again, we're working in the plane, so all of these forces exert torques on the center of the wheel that point either in or out of the screen. But the support force and the mg of the pulley don't contribute to the torque since they're at the center. So really, we just have the two tension vectors exerting opposing torques. So when we sum these forces, I'm going to do this on the upper right-hand side here. You got, you got T1 equals M1A. Okay, again, you could include that Y component too, N minus M1G equals 0, but that's not relevant. Then you have T2 minus M2G equals minus M2A. Again, that's the net Newton's laws for the hanging mass, which, by the way, if this, it doesn't matter if one was moving to the left or moving to the right. In all cases, without any friction on this surface, one's always accelerating to the right, two is always accelerating down. So that's going to leave this third block. Now, how many equations describe the dynamics of the pulley? There's technically 3. There are the net forces, and if we had to find the support force, we'd certainly include that. But once again, the net forces aren't relevant to this problem. All that matters is the torque. And so if we look at this wheel here, in keeping with the standard XY coordinate system, you have that, well, T1 will exert a positive torque. Okay, and there's no harm in redrawing it and verifying it for yourself, right? So I redraw it like this, T1, okay, that would obviously, it's not a good vector, that would obviously make the wheel want to rotate counterclockwise, excuse me. And so the tau 1 is positive. And similarly, maybe anti-similarly, T2 would tend to make the wheel rotate clockwise, and so it exerts a negative torque. And so how you would write the net torque equation for that pulley, similarly to these two equations for the forces, would be like this: plus T1R minus T2R equals Newton's second law for rotational dynamics says that the sum of the torques equal the moment of inertia about that axis times the angular acceleration. And since the T2 is bigger than T1, it exerts a larger torque, and so the acceleration should be in the same direction as the torque. something that the book kind of stresses. The book doesn't really get to it to the end of the chapter, but angular accelerations and angular velocities are also vectors. If you think of the merry-go-round, if you think of the thing rotating, then this thing rotating, it is definitely, no, it is characterized by an angular velocity vector. And if you point your thumb in the direction of the angular velocity vector, your fingers will curl in the actual rotation of the object. So this is a slightly, not off topic, but a bit of an aside. If the rotation increases, then alpha is a vector that points in the direction of omega. If the rotation decreases, then alpha points against the rate of rotation. It's also possible that alpha can point in a direction completely opposite of omega, completely perpendicular, but that's for another section. So in this case, on the pulley, the torque points into the screen, which is going to make that negative. That angular acceleration also points into the screen, which is going to make that negative as well. That's why I have negative sign there. And so if you look at these three equations, you're usually given the mass and the gravity and the radius and all the parameters. You can calculate the moment of inertia, look it up in the table. How many unknowns do you have? Well, technically you got acceleration and you got T1 and T2 and you have alpha. So you have 4 unknowns. So by itself, we can't solve the problem. But this is where the acceleration constraint comes in. The idea, and I'm going to draw it with this slightly different color. Just going to find it. Yeah, right here. I'm going back to this picture here at the very top. The acceleration of every point on the rope is down, or it's in this direction. And that acceleration vector kind of wraps around the edge of the pulley, or the drum, or whatever you want to call it. And it continues all the way like this. So this is the acceleration vector of the rope at every location of the rope. It's all accelerating with the tangential magnitude of the same rate. So the pulley is increasing its rate of rotation while the rope is increasing its velocity. And so if you just look at that if you look at that picture, you see that the angular acceleration is related to the tangential acceleration. Just like the angular velocity is related to the tangential velocity, and it's related in magnitude in the simple way A equals R alpha. That is in the case of constant R, which of course we don't really do anything but constant radii, just circles. So we can use this. This is called the constraint for rolling without slipping. Right? It's really derived from the rolling without slipping constraint, which says that for an object on the street, if the car is moving at a certain speed, then the wheel has to be rotating at a specific rate. More on that in the rolling motion section. But so we can make that substitution. We can turn alpha into A over R. Cancel that and instead write A over R. And then the other thing that we can do to this the third equation on the upper right-hand side is generally the moment of inertia for basic objects can be expressed in terms of the mass of the object times the radius squared times some number, which that number is usually 0.5, 1, 2/3, 0.4, 2, depending on the nature, depending on not only the depending on the way that the mass is distributed, but also where the axis is on the rigid body. And so that number, let's say for a disk, if it's a disk, we can just say that it's 1/2. So I'll just do 1/2 and just say, okay, that's for a disk, for a solid cylinder. Soda can, filled soda can, pop can. So the I then becomes, well, let me just rewrite this equality. I just rewrite this whole equation actually. Well, on the right-hand side, we have minus, give myself more room, minus 1/2 mr squared times A over R. That's the left-hand side. The right-hand side. The left side is still T1R minus T2R. And so something miraculous happens in that the mass doesn't, or the radius goes away. Because on the right-hand side, you have the r squared in the numerator from the moment of inertia, and then you have the a over r, the r in the denominator from the rolling without slipping constraint. So all the r's cancel, and you're left with really a third equation similar to these two at the top. T1 equals m1a, T2 minus m2g equals minus m2a, which is just T1 minus T2 equals minus 1/2 big M times A. So with all of that, we can substitute for T1 and T2 to solve for our acceleration. And hopefully our acceleration is something similar to what we just got. So I'm going to rewrite those equations. I'm going to delete everything, rewrite them. So we have T1 equals M1A. So even if you were struggling following along with all the steps, you can certainly reset right now and solve these equations for A. T1 minus T2 equals minus 1/2 M times A. So how am I going to solve this? Well, I would just solve the second one for T2 and then subtract 1 from 2. Right, so T2 equals plus M2G minus M2A. So when you subtract those two, you get, with the substitutions, you're going to get M1A, that's T1, minus T2, which is M2G minus M2A, over here, equals, on the right side, minus 1/2 M times A. Right, and so it looks to be easiest, if we're trying to solve for A, it looks to be easiest to get the A's on the left side, because it'll be positive, and get the everything else to the right-hand side. You can see how this works, and skipping, doing some algebra and collecting like terms, you get that the acceleration is m2 divided by m1 plus m2 plus 1/2 m, capital M, times g. And that is the acceleration of the system when you include the mass of the pulley. So a couple remarks on this equation that we just derived. It reduces to, so as the mass goes to 0, or as the moment of inertia goes to 0, or both, this term goes away. And then it looks exactly like the acceleration of the two-block system with the massless pulley. And so that's very encouraging that it reduces to the equation that we already knew. Again, capital M is the mass of the pulley. Why is there 1/2 right there? It's because we assumed that the pulley was shaped like a disc. If we assumed that it was shaped like a ring, then the acceleration would be, it'd be a 1 times capital M. If we were able to somehow thread it around a bowling ball, then it would be 2/5 times capital M. So that 1/2 isn't special, it's just the specific form of the shape of the object that we took. And of course, then you can calculate tensions as well. It's not, I mean, that's just more calculations to do. But this is a great example of how rotation, you can use rotational dynamics to extend the types of problems you can do from problems that you already know.